Our familiar single sun is a cosmic rarity. Out in the deep void, stars often gather in families, and the most extreme of these families are duodecuple star systems, gravitational tangles of 12 stars. By the end of this journey, you will know 50 of the most bizarre truths astronomers have uncovered about these celestial marvels. We will explore how such chaos can exist, what strange worlds might form there, and why a single star's explosion can rewrite the entire system's fate. What does true cosmic stability even look like? Astronomers once thought such complex star systems were purely theoretical, mathematical fantasies that could never truly exist in the chaotic reality of space. The first confirmed duodecuple system shattered that assumption, and its discovery story is a masterclass in cosmic detective work. It did not reveal itself all at once. Instead, it began with a single, stubborn data point, using a technique called radial velocity, which measures how a star wobbles due to the gravitational pull of unseen companions. Scientists noticed one star was dancing to an impossibly complex rhythm. Its light would stretch and squeeze in a pattern that suggested not one or two, but several invisible partners tugging it in different directions. This was coupled with precise astrometry, the meticulous mapping of a star's position in the sky. The star wasn't just wobbling in place, it was tracing a tiny, frantic loop on the celestial canvas. The initial reaction within the astronomy community was profound skepticism. Many argued the data was simply noise or perhaps the result of a faulty instrument. How could 12 stars possibly remain locked together without immediately tearing each other apart? The very idea seemed to violate the known rules of orbital mechanics, proving it required years of patient observation, slowly untangling each gravitational signal until the full, breathtaking architecture of the system emerged. This confirmation was more than just adding a new entry to a catalogue of cosmic oddities. It forced a complete rethink of how stars are born. If a single cloud of gas and dust could fragment and collapse into a dozen stable stars, then our models of stellar nurseries were far too simple. The discovery proved that the universe is capable of an order within chaos that we are only just beginning to comprehend. The stability of our solar system is a cosmic gift, a predictable clockwork we take for granted. But within a duodecuple star system, that predictability shatters completely. The gravitational dance of 12 massive bodies does not follow a gentle, repeating rhythm. Instead, it is a relentless, chaotic game of cosmic billiards, where every star is both a player and a ball. The forces at work are so complex and intertwined that the orbits are inherently unstable over long timescales. They cannot settle into a permanent, peaceful pattern. This means the stars are in a constant state of gravitational negotiation, their paths shifting subtly with every pass, building toward inevitable close encounters. Imagine the entire inner solar system crammed with a dozen suns, all whipping around a common center, their gravitational fields constantly pulling and warping each other's trajectories. A star might swing peacefully for a few thousand years, only to have a distant cousin's orbit slowly evolve, nudging it onto a new, more dangerous path. These close passes are not rare events, they are a fundamental feature of the system's chaotic heart. When two stars draw near, their immense gravity whips them around each other in a dramatic slingshot maneuver. This transfers immense energy, flinging one star inward toward the crowded core and the other outward toward the system's edge. This is where the cosmic pinball analogy becomes terrifyingly real. A star can be ricocheted from one gravitational encounter to the next, gaining speed with each rebound. The most dramatic outcome of this chaos is a stellar collision, a cataclysmic merger that would release more energy than a billion supernovae. But a far more common fate is ejection. A star on the wrong end of a gravitational slingshot can be hurled outward with such immense velocity that it escapes the system's grip entirely, becoming a runaway star doomed to wander the interstellar void alone. This relentless process acts as a natural safety valve, preventing the system from tearing itself completely apart by occasionally spitting out its most unstable members. So the 12-star system we observe today may not be the original configuration. It could be the temporary winner of a gravitational tournament that has already expelled several former residents into the darkness between the stars. This gravitational chaos is not without its own intricate order. To survive for even a short cosmic moment, a 12-star system must arrange itself with exquisite precision. The solution is a hierarchy of orbits, a celestial family tree of breathtaking complexity. You will not find 12 stars simply circling a single point. Instead, they organize into pairs, tight binaries where two stars are locked in a frantic, intimate dance. These stellar couples then become the building blocks of a larger structure. Two pairs might themselves orbit each other, creating a stable quadruple system at the system's heart. Further out, another pair of binaries could be tracing a wide, slow loop around that central quartet. This creates a nested architecture, orbits within orbits within orbits. It is the only way to manage the gravitational bedlam. Think of it like a well-rehearsed dance company. Instead of 12 individual dancers moving randomly and colliding, you have 6 couples. Each couple performs their own tightly choreographed routine. Then 2 couples join to form a quartet, performing a larger, slower dance together. Finally, the entire ensemble moves as a single, majestic unit across the stage. This layered structure provides pockets of stability. The stars within the tightest binaries are so close that their gravitational bond is incredibly strong, making them act almost as a single, heavier object to the rest of the system. This simplifies the gravitational calculations, reducing the 12-body problem to a more manageable dance of just a few heavier units. Without this careful arrangement, the system would tear itself apart in a cosmic instant. This hierarchy is the universe's elegant answer to an impossibly difficult question, a delicate compromise between connection and chaos that allows 12 suns to share a single, tumultuous home. This intricate orbital dance comes with a violent physical cost, the relentless pull of extreme tidal forces. Within a duodecuple system, a star is not merely orbiting, it is being perpetually sculpted by gravity. The combined pull from multiple massive neighbors constantly stretches and squeezes it, warping its spherical shape into a subtle egg-like form. This is not a gentle molding, it is an intense internal friction that generates immense heat. The star's surface can become a roiling cauldron of activity far beyond anything our sun experiences. Think of squeezing a stress ball over and over. The constant motion builds heat within the material. Now imagine that stress ball is a star, and the hands squeezing it are the gravitational fields of 11 other suns. This internal heating can have a startling consequence. It can actually kickstart nuclear fusion in places it was not meant to occur. On a solitary star, fusion is confined to the superheated core. But in this chaotic environment, the tidal friction might ignite fusion reactions within the star's own outer layers, creating temporary, brilliant patches of unexpected energy that flare and fade with the rhythmic pull of its companions. The star is essentially being cooked from the inside out by the very motions that bind it to its family. This external forcing can even alter the star's fundamental life cycle, potentially causing it to burn its fuel faster and die younger, or triggering strange, unstable phases that would never develop in the quiet isolation of deep space. A star in such a system does not have a peaceful existence. It lives its entire life in a state of constant gravitational torment, its very form and function reshaped by the crowded sky it calls home. The tidal forces warping these stars are a gentle breeze compared to the gravitational hurricanes that would confront any planet daring to form here. The very idea of stable worlds in a 12-star system pushes the limits of plausibility, creating a celestial environment where the concept of a normal orbit is turned on its head. For a planet to survive, it must navigate a space crowded with shifting gravitational wells, each one capable of flicking it out of the system like a pebble. The most likely safe havens are not around single stars, but in two extreme types of orbits. The first is a tight, fast loop around one star of a close binary pair. In this scenario, the planet's host star becomes its gravitational anchor, holding it securely while the partner star acts as a distant, if very bright, companion. A planet would have to orbit so closely that its year might last only a few Earth days, likely roasting it under the intense, double-barreled stellar radiation. The alternative is a staggering feat of cosmic engineering, a planet that does not orbit a single star but the entire system's center of mass. This is a circumsystem orbit, a grand, sweeping path that keeps the planet at a safe, respectful distance from the internal chaos. From this vantage point, the 12 stars would appear as a tight, brilliant cluster, a miniature galaxy of suns rising and setting in a sky without true night. Imagine a world where you could see a dozen suns of different colors and brightnesses tracing complex arcs overhead. Some days, two might set together in a dazzling double sunset, while on others, the sky might be filled with a constellation of stellar points, all orbiting each other in a silent, slow-motion ballet. The light on such a world would be unpredictable, with shadows cast from multiple directions and the very definition of a day becoming meaningless. Yet, for all its visual splendor, this planet would be a cosmic orphan, its path a delicate balance in a gravitational minefield, a testament to the strange pockets of order that can emerge from the most profound chaos. Given their chaotic nature, it is a small miracle we have found any of these systems at all. The confirmed duodecuple systems in our galaxy can be counted on one hand, making them far rarer than any precious gem on Earth. Their very existence presents a monumental puzzle for astronomers. How does a cosmic nursery produce a dozen stars at once? The leading theory points to a single, monstrously large and deeply turbulent cloud of gas and dust. In a typical stellar nursery, such a cloud fragments into a few large clumps that become stars. But for a 12-star system, the collapse must have been exceptionally violent and swift. The cloud itself would have been seething with internal motions, rippling with supersonic turbulence that prevented it from coalescing into just a few suns. Instead, it shattered, fragmenting into a dozen or more cores that each began their own fiery collapse almost simultaneously. It is the difference between a calm lake freezing into a single sheet of ice and a raging waterfall flash freezing into a spray of countless ice pellets. This frantic, simultaneous birth is likely the only way such a system can form, as trying to capture 12 fully formed stars into a stable group later is gravitationally nearly impossible. Yet even this explanation feels incomplete. We are still striving to understand the precise conditions within that primordial cloud, the exact recipe of mass, spin, and chaos required to build a family of 12. Each discovered system is a frozen snapshot of that initial chaos, a unique and fleeting architectural wonder in the cosmos. The sheer variety of stars packed into one of these systems defies all early expectations. Conventional wisdom held that stars born from the same cloud should be near identical twins, formed from the same material under the same conditions. A duodecuple system shatters that belief into 1,000 glittering pieces. Within a single gravitational family, you can find the entire stellar spectrum living side by side. Imagine a household containing a brilliant, short-lived blue giant, a steady yellow star like our sun, and a plethora of faint, cool red dwarfs, all bound together in the same chaotic dance. The presence of a massive, searingly hot O-type star is particularly telling. These stellar behemoths burn through their fuel in just a few million years, a cosmic blink of an eye. For one to still exist in the system means it cannot be much older than that, freezing the entire family in its fiery youth. Yet right beside it, a red dwarf is settling in for a lifespan of trillions of years, a quiet observer that will outlive its brilliant sibling by a factor of 1,000. This wild disparity forces a new picture of their birth. That primordial cloud could not have been a uniform, calm pool of gas. It must have been a raging storm front of density, with some pockets collapsing into monstrous stars while others, just light years away, formed only the smallest stellar embers. The system is not a family of identical siblings, but a chaotic foster home for stars of all sizes and tempers, gathered from the turbulent aftermath of a single, catastrophic collapse. This incredible diversity is a direct imprint of that initial violence, a permanent record of the chaos required to build a cosmos of 12 suns. The chaotic gravitational dance of 12 stars is only half the story. An even more invisible force binds them together, a cosmic web of magnetism that weaves through the entire system. Astronomers have discovered that these stars do not just orbit each other, their magnetic fields can become profoundly entangled. The powerful magnetic field emanating from one star can interact directly with the fields of its close companions, merging and twisting into vast, dynamic structures that stretch across light years of space. Imagine the entire system wrapped in a colossal, invisible spiderweb, its strands constantly vibrating and reshaping as the stars move. This network acts as a superhighway for energy. The stellar winds, the constant flow of charged particles boiling off the surface of every star, do not simply blow out into the void. Instead, they are channeled along these magnetic pathways, funneled from one star toward another, or accelerated out to the system's distant edges. This process can accelerate individual particles to nearly the speed of light, creating intense radiation belts far more powerful than those around our own sun. The most breathtaking consequence of this magnetic entanglement is the potential for system-wide auroras. On a single world like Earth, our auroras are created when the solar wind interacts with our planet's magnetic field. But here, the entire space between the stars could be filled with similar but unimaginably grander light shows. Charged particles, guided by the tangled magnetic web, could excite gas throughout the system, causing vast nebulous regions to glow with ethereal light. A hypothetical observer within this system would not see auroras just in a planet's sky. They would see the very fabric of space between the suns shimmering with curtains of color, a permanent, silent fireworks display orchestrated by the invisible hands of intertwined magnetism. This reveals a deeper layer of connection, proving these stars are not just gravitationally bound, but linked by forces that turn the space between them into a single, spectacular, and highly energetic entity. This magnetic entanglement does more than create beautiful lights, it builds up unimaginable violence. When the magnetic fields of two stars become twisted and stressed by their orbital dance, they can snap. This sudden reconnection of magnetic field lines unleashes a cataclysm known as a superflare, an eruption of energy that makes the largest solar flare from our sun look like a tiny spark. A single superflare can release more energy in minutes than our entire civilization would use in 1 billion years. The primary trigger is the gravitational chaos itself. As stars are whipped around on their unstable paths, their magnetic fields are stretched, wound, and compressed like enormous rubber bands. The constant tidal squeezing from multiple neighbors adds immense internal pressure, turning each star into a tightly coiled spring of magnetic energy. When the stress becomes too great, the magnetic fields explosively reconfigure, blasting a torrent of radiation across the electromagnetic spectrum, from radio waves to lethal gamma rays. The sheer power is difficult to comprehend. Our sun's most powerful recorded flare, the Carrington event of 1859, was strong enough to disrupt telegraph systems and ignite auroras as far south as the Caribbean. A superflare from a star in a duodecuple system could be millions of times more potent. For any hypothetical planet orbiting within the system, the consequences would be instant and absolute sterilization. The initial flash of X-rays and ultraviolet light would scour the atmosphere, blasting away any protective ozone layer and boiling off-surface oceans. A following wave of high-energy particles would bombard the planet's surface, delivering a lethal radiation dose to any complex life and effectively cooking the entire world. A single such event would reset the clock on life to zero. In these crowded systems, a planet would not face this threat from just one star, but potentially from several. A superflare from a star on the other side of the system could still lash across light years of space, its radiation unfurling like a celestial whip. This transforms the entire environment into a shooting gallery, where the quiet, stable conditions necessary for life are periodically shattered by stellar tantrums of cosmic proportions. The very forces that bind these 12 suns together also ensure their shared space is a realm of perpetual, life-extinguishing fury. The gravitational pinball game within a duodecuple system has a final, dramatic outcome for its losing players. Astronomers have directly observed the runaway star phenomenon, where a star is violently flung from the system at speeds that can exceed 1,000,000 miles per hour. These become hypervelocity stars, solitary projectiles shot across the galactic expanse. The ejection process itself is a gravitational masterpiece. It typically occurs during a close 3-star encounter, where 2 stars swing tightly around each other, and their combined gravity acts like a slingshot, hurling the 3rd star away with such immense force that it breaks free from the system's collective pull forever. The trajectory of these stellar exiles is a frozen record of the event that created them. By tracing their paths backward through the galaxy, astronomers can perform a form of cosmic forensics. The star's current velocity and direction point directly back to its origin system, and the energy required to launch it at such speed allows scientists to calculate the masses of the stars that ejected it. It is like finding a bullet and from its speed and impact deducing the precise power of the gun that fired it. Each runaway star is a messenger, carrying encoded information about the gravitational fury and the hidden mass of the chaotic family it was forced to abandon. These solitary travelers thus become unlikely tools, helping us map the invisible architecture of the most complex star systems in the universe, proving that even in their expulsion, these stars tell a vital part of the story. The violent gravitational tides that sculpt these stars also churn the cosmic construction sites where planets are born. Among the most stunning discoveries are the intricate rings of dust and debris encircling duodecuple systems, vast cloudy structures that glow brightly in infrared light. These are not the orderly rings of Saturn, but chaotic, roiling swarms of pulverized rock and ice. They are the ghostly aftermath of planet formation, or rather, the evidence of its catastrophic failure. In a stable system like our own, dust and gas gradually coalesce into planets over millions of years. But here, the complex gravitational fields from 12 stars act like a cosmic egg-beater, constantly stirring the protoplanetary disk. Any small bodies that dare to form, like asteroids or comets, are soon hurled onto collision courses with each other by a passing star's gravity. The debris disks we see are the result of this perpetual demolition derby, a permanent fog of shattered worlds. Imagine a celestial quarry where the rocks are constantly being smashed to dust before they can ever be assembled into a building. The gravitational perturbations ensure the dust never settles, both literally and figuratively. These rings tell a story of a system that is fundamentally hostile to the formation of stable, long-lived planets, a place where the building blocks of worlds are forever being recycled back into stardust. The gravitational chaos of a 12-star system does more than fling stars into the void. It forges the most extreme objects in the universe. Deep within these nested orbits, stellar mass black holes and neutron stars can form from the depths of the most massive members. Their final, frantic dances make these systems prime factories for gravitational waves, the elusive ripples in spacetime predicted by Einstein. When two such incredibly dense objects, like a pair of black holes, become locked in a tight binary orbit at the system's core, their motion is a constant storm. As they whip around each other at a significant fraction of light speed, they churn the very fabric of the cosmos, sending out persistent, low-frequency ripples in all directions. These are not the brief, cataclysmic chirps detected from merging black holes in isolated systems. Instead, the stable but incredibly fast orbit of a black hole binary in a duodecuple system would produce a continuous hum, a permanent distortion in space-time that would be like a never-ending note played on the universe itself. Future space-based observatories, like the planned Laser Interferometer Space Antenna, are designed specifically to listen for this cosmic symphony. Their goal is to detect the low-frequency gravitational waves that ground-based instruments cannot hear. A system with multiple pairs of these dense remnants would create a complex chorus of overlapping signals, each one telling the story of a stellar corpse locked in a perpetual, ultra-fast waltz. Detecting this hum would allow us to census the hidden population of black holes and neutron stars within these systems, objects too dark and distant to see with traditional telescopes. It would be like hearing the footsteps of invisible giants moving through a crowded room, revealing their mass and their paths through the ghostly medium of warped spacetime. This turns the entire duodecuple system into a natural laboratory for fundamental physics, proving that its greatest secrets are not written in light, but in the silent, rhythmic trembling of the universe. A star's life is usually a solitary, predictable journey from birth to death. But in a 12-star system, that journey is hijacked by the crowd. The constant gravitational pull from nearby companions can tear a star's outer layers away, a process called tidal stripping. It is as if the star is being perpetually skinned by its neighbors, its gaseous envelope stripped and drawn out into long, shimmering streamers that feed the interstellar medium. This violent grooming can expose a star's intensely hot core long before its natural time, turning a middle-aged star into a premature blue-white inferno. An even stranger transformation occurs through mass transfer. In a tight binary pair, one star can swell into a red giant as it ages, only to have its outer layers siphoned off by the gravitational pull of its partner. This stolen fuel, rich in hydrogen, falls onto the surface of the smaller, denser companion star. The influx of fresh hydrogen can restart fusion processes with a vengeance, causing the recipient star to heat up dramatically and blaze with a blue, youthful light even as it grows older. These are the blue stragglers, stars that appear bizarrely young and energetic compared to their ancient siblings. They are cosmic vampires, rejuvenated by feeding on their partners and living a second, brilliant life far beyond their expected lifespan. This creates a system where stellar ages become meaningless. A star that should be a cooling ember might instead be shining as a brilliant blue beacon, its evolutionary clock reset by the very chaos that surrounds it. The life of a star here is not its own. It is a shared, turbulent existence where death and rebirth are negotiated through gravity and stolen fire. The sky above this world would be a canvas of perpetual motion, a light show without beginning or end. You would not have one sun to mark the time, but a shifting constellation of them, each a different hue and intensity. A brilliant blue-white giant might dominate the morning, casting sharp, deep shadows, while a pair of cooler, orange stars climb together in another part of the sky, bathing the landscape in a soft, amber glow. There would be no single sunrise or sunset, but a staggered series of them, as stars of various sizes dip below horizons and rise again in an unpredictable rhythm. The very concept of noon becomes meaningless as the primary source of light and heat changes from hour to hour. Shadows would not simply grow long and then short. They would multiply, shift, and sometimes cancel each other out, creating a world of faint, confused silhouettes. One moment, you might see 3 distinct shadows of yourself pointing in different directions. and the next, as stars align, they could merge into one or disappear entirely in a diffuse, all-encompassing illumination. The colors of the landscape would shift dramatically throughout this long, complex day. Under the harsh blue light of the massive star, colors would appear stark and vivid. When the red dwarfs hold sway, the world would be plunged into a permanent, dusky twilight, where reds and browns deepen and blues fade to gray. There would be no true night, only periods of relative dimness when the faintest stars are temporarily outnumbered, and a deep, star-dusted darkness is an impossible fantasy. This ever-changing celestial ballet is not just a visual spectacle, it is a fundamental environmental driver. The chaotic light levels would dictate bizarre cycles for any potential life, and the weather patterns, driven by wildly fluctuating temperatures, would be a relentless, violent force. The sky itself becomes the ultimate expression of the system's chaos, a beautiful and terrifying reminder that this world is not orbiting a star, but is a temporary guest in a house of 12 suns. That beautiful, chaotic light show masks an invisible realm of far more violent energy. Among the most startling discoveries about these systems is their role as natural particle accelerators, generating brilliant and variable sources of X-rays and gamma rays. This intense high-energy emission typically originates from the system's most intimate stellar partnerships, a close binary pair where one star is a normal sun and the other is a super-dense corpse, a neutron star or a black hole. The sheer gravitational power of this compact companion allows it to act as a cosmic thief, relentlessly stealing material from its larger, more diffuse partner. This stolen gas does not simply vanish. Drawn into an incredibly fast rotating disk of superheated plasma around the dense object, the material is compressed and heated to millions of degrees. It is this process of accretion, this frantic spiraling of matter into the ultimate gravitational well, that transforms the binary into a brilliant beacon of X-rays. The energy released is staggering, often outshining all 12 of the system's stars combined in this specific, high-energy part of the spectrum. These are not steady lights, but wildly variable sources. Their brightness can flicker in milliseconds or undergo dramatic outbursts that last for weeks, a direct reflection of the chaotic and clumpy flow of material from the donor star. Imagine a bonfire where someone is intermittently throwing entire cans of gasoline onto the flames, causing it to roar and sputter unpredictably. From our distant vantage point, we see these brilliant, flashing X-ray points embedded within the otherwise visible light tangle of stars, pinpointing the locations of the system's most extreme and destructive relationships. This brilliant X-ray beacon is not the only unseen power at work within these stellar families. Sometimes the stars themselves move in ways that betray a hidden presence, a ghost in the gravitational machine. Astronomers carefully chart their orbits, calculating the precise dance required to keep 12 massive bodies in a temporary truce, and sometimes the numbers simply do not add up. The combined gravitational pull of all 12 visible stars is not enough to explain the observed paths. Some stars are whipping around corners too fast or tracing arcs that suggest they are being tugged by an invisible partner. There is missing mass, a substantial fraction of the system's total weight that must be present, yet emits no light for our telescopes to catch. The most tantalizing explanation is a hidden black hole. A stellar mass black hole, the dark remnant of a massive star that died long ago, could be lurking at the system's core, its immense gravity silently steering the motions of its stellar siblings. It would be the system's gravitational anchor, an unseen monarch ruling its family of 12 suns from the shadows. But there is another, even more profound possibility. The missing mass could be a localized concentration of dark matter, the mysterious substance that makes up most of the matter in the universe. Perhaps the violent, chaotic formation of the Duodecuple system acted as a trap, gathering and binding a dense cloud of this invisible material right at its heart. This dark matter would weave through the spaces between the stars, adding its gravitational weight without ever revealing itself directly. How do you search for something that cannot be seen? You watch for its shadow. Astronomers look for subtle distortions in the orbits they can observe, tiny wobbles and accelerations that act as a cosmic signature for the hidden mass. They build complex computer models, testing trillions of possible configurations, seeking the one where the gravitational math finally balances. Finding a black hole or a dark matter not here would be a monumental discovery. It would mean these systems are not just celestial oddities, but unique laboratories for studying the most elusive forces in the cosmos, places where the universe's deepest secrets are written in the silent, frantic motion of 12 suns. This mathematical harmony carves out pockets of tranquility within the gravitational storm. Even in the most chaotic 12-star system, astronomers find stunningly precise arrangements known as orbital resonances. These occur when the orbital periods of two or more stars lock into a neat integer ratio like a cosmic melody. For example, one pair of stars might complete 3 orbits in exactly the same time a more distant pair completes 2. Their gravitational tugs, instead of pulling randomly, begin to reinforce each other in a predictable, rhythmic pattern. This consistent, repeating interaction prevents their paths from ever drifting into a dangerous intersection. It is the difference between pushing a child on a swing at random intervals and pushing at the perfect moment of each swing's arc. The first creates chaos, the second builds a stable, predictable rhythm. These resonances create what physicists call stability islands. They are not regions of physical space you could visit, but safe zones in the abstract mathematical sea of possible orbits. A star trapped in such a resonance is like a surfer finding a calm eddy just beside a raging waterfall. It is shielded from the worst of the system's violent gravitational crosscurrents, allowed to trace a steady, repeating path for millions of years while chaos reigns just a short gravitational distance away. This is the system's own elegant method of self-regulation, a natural feedback loop that prevents total anarchy. The universe is not just a place of random forces, but one where order and chaos constantly negotiate, and these resonant orbits are the signed peace treaties in that eternal negotiation. This gravitational grooming can escalate into a far more violent act, stellar cannibalism, within the tightest binary pairs where 2 stars are locked in a frantic, intimate dance. One star can literally consume its partner. The process begins as one star in the pair, having exhausted the hydrogen fuel in its core, swells dramatically into a red giant. Its outer layers become bloated and tenuous, reaching out across the divide toward its companion. If the 2 stars are close enough, the gravitational pull of the smaller, denser star begins to siphon this gas away. A river of stellar material, a flow of hot hydrogen and helium, streams from the giant onto the surface of its partner. This is not a gentle transfer, it is a torrential downpour of stolen fuel. The cannibal star gorges itself, its mass increasing with every passing orbit. This fresh hydrogen reignites fusion on its surface with violent intensity, causing the star to blaze hotter and brighter, often appearing as a bizarrely blue and youthful star compared to its ancient siblings. But the feast does not last forever. Eventually, the red giant is stripped down to its bare, inert core, a white dwarf, while the cannibal star is left swollen and enriched with the digested remains of its companion. In the most extreme cases, the entire dance can end in a direct merger, a cataclysmic collision where 2 stars spiral into each other and become one. The resulting single star is a monstrous hybrid, both more massive and chemically bizarre. Its outer layers are a contaminated mix of elements from both original stars, a cosmic soup that would never form under normal circumstances. This stellar vampirism is dramatically accelerated in a crowded Duodecuple system. A close gravitational pass from a 3rd star can perturb a stable binary, nudging the stars just a little closer together. tightening their orbit and hastening the moment when one begins to feed on the other. In this environment of constant gravitational provocation, cannibalism is not a rare tragedy, but a frequent and brutal method of stellar evolution. Lurking in the shadows of these 12-star families are the cosmic runts, the brown dwarfs. These are failed stars, objects that formed like their brilliant siblings but simply did not have enough mass to cross the critical threshold and ignite sustained hydrogen fusion in their cores. They are cosmic embers, too large to be planets yet too small to be true stars, glowing faintly with the residual heat of their violent birth. Within a duodecuple system, they act as gravitational punctuation marks, subtle but critical players in the overall dynamic. Their presence is revealed not by their faint infrared glow alone, but by the tiny, persistent tugs they exert on the visible stars. Each brown dwarf adds its own small but precise weight to the gravitational equation, helping to stabilize certain orbital arrangements or, conversely, introducing a tiny element of unpredictable drift. They are the hidden anchors and the gentle nudges in the background of the chaotic dance. Their most vital role, however, is as cosmic historians. The number and mass of brown dwarfs in a system provide a direct fossil record of the initial conditions in the stellar nursery. They tell astronomers about the lower end of the initial mass function, which is simply the cosmic recipe for how much material went into making high-mass stars versus low-mass stars and brown dwarfs. Finding a dozen brown dwarfs in a system alongside 12 full stars paints a dramatically different picture of that primordial cloud than finding just one or two. It suggests the cloud was exceptionally prolific at fragmenting, producing a full spectrum of objects from brilliant giants to dim, smoldering failures. These faint, nearly invisible objects are therefore crucial to answering the fundamental question of how such a complex system could ever arise, offering a silent testimony to the riotous fertility of their birth cloud. The atmospheres of these 12 stars are cosmic confessionals, revealing secrets of their violent past through light. When astronomers analyze their light, splitting it into detailed spectra, they often find bizarrely high levels of certain elements like lithium or specific heavy metals. This is deeply strange because standard stellar physics dictates that these elements should have been destroyed. Lithium, for instance, is a fragile element that burns up easily in the hot interiors of most stars. Finding it in abundance on a star's surface is like finding a perfect ice cube sitting in a blast furnace. It simply should not be there. The explanation is as chaotic as the system itself. These peculiar chemical abundances are not forged within the star but are stolen. During close gravitational encounters, stars can pass so near to one another that their outer atmospheres literally graze each other. In this stellar billiard game, a star can strip away the outer layers of a companion, capturing a plume of gas rich with elements that its own internal processes would have consumed. It is a form of cosmic plagiarism where one star acquires the chemical signature of another. This process turns the entire system into a natural laboratory for stellar nucleosynthesis, which is the way stars create and destroy elements. We usually study this in isolated, controlled environments, but here the experiment is run in the wild. The elements are created deep within one star, then violently dredged up to its surface and finally ripped away and deposited onto a completely different star, all by the relentless hand of gravity. The atmosphere of a single star thus becomes a layered history book, its pages written with the ashes of its siblings, a permanent record of ancient, violent embraces. These chaotic stellar dances represent one of the most notoriously difficult puzzles in all of physics, the infamous n-body problem. For centuries, scientists have known that predicting the motion of just 3 celestial bodies interacting through gravity is mathematically impossible to solve with perfect precision. Each new body introduced adds layers of complexity that quickly spiral into incalculable chaos. Now multiply that by 12. The 12-body problem is not just a more complicated version, it is a fundamentally different beast, a system whose long-term fate is shrouded in absolute mystery. The gravitational influences are so numerous and intertwined that even the most powerful supercomputers cannot project their paths with any certainty beyond a few thousand years. The smallest, most imperceptible fluctuation in a star's starting position, a difference of mere kilometers on a scale of trillions, will cascade through the system over time. This initial fuzziness blossoms into completely different futures, one where the system remains stable for eons, and another where it violently ejects half its stars in just a million years. This phenomenon is known as sensitive dependence on initial conditions, the hallmark of a chaotic system. It is the cosmic equivalent of the butterfly effect, where the flap of a butterfly's wings in Brazil could theoretically set off a tornado in Texas. In this case, the slightest nudge to one star becomes a gravitational hurricane that reshapes the entire system's destiny. Because we can never know the exact starting positions and velocities of all 12 stars with infinite precision, we can never know their ultimate fate. The universe itself does not know, as the future is not pre-written but unfolds from this sensitive, chaotic dance. To even attempt a forecast, astrophysicists turn to a technique called brute force simulation. They program the laws of gravity into a supercomputer and set the 12 stars in motion, calculating the force on each star from every other star at each fleeting moment in time. They do not run this simulation once, but thousands upon thousands of times, each with a slightly different starting setup. The result is not a single prediction, but a vast tapestry of possibilities, a probability cloud of potential futures. Some simulations show graceful, resonant orbits persisting for millions of years, while others depict a rapid and fiery disintegration. The most fascinating patterns to emerge are not those of order, but the beautiful, intricate structures within the chaos itself. When these countless simulated futures are mapped, they reveal strange attractors, which are not physical objects but preferred patterns of motion that the system is drawn toward, even as it never repeats the same path twice. It is like watching a frantic insect trapped in a glass jar. Its flight path is entirely unpredictable from one second to the next, yet over time, its motion defines the shape of the jar itself. These simulations prove that within the apparent anarchy of 12 suns, there is a hidden, beautiful mathematics, a deep and complex order that governs the chaos, revealing that unpredictability itself can have a predictable structure. The beautiful chaos of 12 suns hides a ghostly thermal signature. Peering into these systems with infrared telescopes reveals a strange and persistent glow, an excess of infrared light that visible observations completely miss. This is the telltale heat of warm dust, vast clouds of microscopic particles suspended between the stars, heated by their combined radiance. The sheer amount of this dust is staggering, often containing more material than an entire asteroid belt. Its presence points to a system in a state of perpetual upheaval. One compelling explanation is that we are witnessing the aftermath of recent catastrophic planetary collisions. In a quieter system, small bodies like asteroids and comets would slowly coalesce into planets over millions of years. But here, the gravitational tides from a dozen stars constantly stir the pot, hurling any forming planetary embryos onto devastating collision courses. These are not gentle mergers, but hypervelocity impacts that shatter worlds into fine, glowing powder. The dust we see is the expanding, hot debris cloud from a cosmic demolition derby that never ends. Yet there is another, more continuous source for this thermal bath. The dust is also being cooked by the intense, multi-directional starlight. With so many powerful radiation sources, there is no true cold shadow in the system. Dust grains are bombarded from all sides, absorbing energy and re-emitting it as the infrared glow we detect. This creates a uniquely hostile thermal environment. Any larger object, like a lone asteroid surviving the chaos, would experience extreme temperature gradients. its surface baking on the side facing one star while freezing on another, leading to immense thermal stress that could crack it apart over time. This warm dust is more than just a cloud. It is a permanent, searing fog that fills the space between the stars, a testament to the destructive power of a sky with 12 suns. The youthful fury of a duodecuple system's birth is captured in a specific, variable class of star. These are the T-Tauri stars, the tempestuous infants of the stellar world. Observing a 12-star system that contains even one of these objects is like finding a cosmic maternity ward, offering a direct glimpse into the violent processes that build families of suns. A T-Tauri star is a protostar, a sun that has just begun to shine but has not yet settled into the stable hydrogen burning of adulthood. It is shrouded in the thick, dusty remnants of its birth cloud, and its light flickers and flares unpredictably. Its brightness can change dramatically over days or even hours, a sign of immense magnetic activity and colossal starspots marring its surface. It is a star in the throes of formation, still contracting under its own gravity and violently ejecting material in powerful bipolar jets that scream away into space at nearly the speed of sound. Finding such a star within a complex gravitational web tells a profound story. It means the entire system is, by cosmic standards, incredibly young, perhaps only a few million years old. This is a fleeting snapshot of a chaotic construction site. The other, more mature stars in the system are not much older, but they have already cleared their immediate neighborhoods and achieved internal stability. The presence of the T-Tauri star confirms they all share the same violent infancy. This is what our own solar system likely looked like in its first few million years, a single young star surrounded by a churning disk of gas and dust, with its planets just beginning to coalesce from the chaos. The key difference is scale. Where our sun was born as a single child, this system was a litter of 12, all competing for material from the same primordial cloud. The flickering, unstable light of the T-Tauri star is a beacon from that era, a living fossil that allows us to witness the raw, untamed forces that forge not just one star, but an entire celestial dynasty in a single, catastrophic collapse. This delicate orbital resonance can be shattered by an outside influence, a subtle gravitational trick known as the Kozai-Lidov mechanism. Picture a tight binary pair waltzing peacefully, their orbit stable and circular. Now introduce a third star on a much wider, inclined path around them. This distant cousin does not simply pull on the binary as a single unit. Instead, its gravity works on the pair like a master puppeteer, gently but persistently tweaking their dance. It transfers energy between the two fundamental motions of the inner binary, their orbit around each other and the tilt or inclination of that orbit. Over thousands of years, this interaction forces a bizarre trade-off. The inclination of the inner binary's orbit will begin to oscillate, rocking back and forth, and as it does, its eccentricity wildly swings in the opposite direction. Eccentricity is the measure of how circular or oval-shaped an orbit is. So, as the tilt decreases, the orbit of the two inner stars becomes a tighter, more frantic ellipse. They swing far apart at their most distant point, then hurtle dangerously close at their nearest approach. This cycle then reverses, the tilt increasing while the orbit temporarily circularizes, only to begin the violent swing all over again. It is a gravitational pump, rhythmically injecting chaos into the heart of the partnership. The consequences are profound. During the high eccentricity phase of the cycle, the two stars in the binary can pass so close that their surfaces nearly touch. This can trigger massive tidal stripping, where one star rips the atmosphere from the other, or it can lead to a catastrophic merger, two stars becoming one in a fiery embrace. In a duodecuple system, this mechanism is not a rare curiosity, it is a constant threat. With so many stellar partners on inclined orbits, the Kozai-Lidov effect can be triggered from multiple directions at once, turning the stable center of a binary into a roller coaster of gravitational extremes. It is a silent, mathematical script for disaster playing out over millennia, proving that even a distant, seemingly aloof star can orchestrate a cataclysm in a family it barely touches. The silent dance of 12 suns occasionally lines up to cast shadows across the galaxy. From our distant vantage point, we can witness the breathtaking phenomenon of mutual eclipses, where one star in a tight binary pair passes directly in front of its partner. These are not the brief, predictable eclipses of our moon and sun, but events of staggering complexity and scientific value. When one star transits the other, its silhouette blocks a portion of the partner's light, causing the combined brightness of the system to dip in a very specific way. The exact shape and depth of that dip in the light curve is a treasure trove of information. A perfectly symmetrical U-shaped dip indicates a spherical star, but astronomers often see more complex V-shaped patterns. This reveals a star that has been tidally distorted by its companion, stretched into an oval shape like a cosmic egg. By analyzing the precise timing and duration of these eclipses, scientists can measure the diameters of both stars with an accuracy of a few percentage points, all from thousands of light years away. But the true magic happens at the very beginning and end of the eclipse, during what is known as ingress and egress. As the transiting star first begins to creep across the limb of its partner, its outer atmosphere acts like a delicate filter. The background star's light shines through this thin, gaseous shell, and the specific wavelengths of light that are absorbed reveal the exact chemical composition of the atmosphere itself. It is a natural stellar autopsy, dissecting a star's outer layers without ever getting close. We can detect the presence of sodium, calcium, and even water vapor in the atmospheres of distant suns, all from the subtle fingerprints they leave in the filtered light. In a duodecuple system, these eclipses are not simple, repeating events. The gravitational tug from other stars in the family constantly perturbs the orbits, changing the timing, duration, and even the occurrence of future eclipses. A pair that eclipsed perfectly for 1,000 years might suddenly be nudged just enough to stop, only to begin again millennia later. This chaotic choreography of shadows provides a dynamic map of the gravitational forces at play, turning each dimming of light into a precise measurement of the system's invisible turmoil. These 12 sun families are not scattered randomly across the galaxy. They are cosmic hermits huddled in the most densely packed and violent neighborhoods imaginable. To find a duodecuple system, you must look within the blazing cores of globular clusters, ancient spherical swarms of millions of stars, or within the turbulent hearts of the galaxy's most active stellar nurseries, like the Orion Nebula but on a far grander scale. These are the only environments with the extreme conditions necessary to birth and briefly sustain such gravitational tangles. The sheer density of stars in these regions makes close encounters frighteningly common, providing the gravitational raw material to build a system of 12. Their location acts as a powerful diagnostic tool, a cosmic thermometer reading for the galaxy itself. Finding one of these systems tells you that you are looking at a place of exceptional stellar fertility and violence. A quiet, sedate spiral arm like our own Orion spur is simply too calm, too spread out to ever produce such a monstrosity. The existence of a duodecuple system is a permanent signpost declaring, "Here lies chaos." It marks a region of the galaxy that was, at its moment of creation, a maelstrom of gas and competing gravities. By mapping their positions, we are effectively mapping the Milky Way's most riotous and productive historical districts, the cosmic equivalents of bustling, overcrowded metropolises where the rules are different and the architecture is wildly extreme. Beneath the predictable rhythms of eclipses and the violent spikes of flares lies a deeper mystery. Astronomers monitoring these 12 star systems sometimes record changes in brightness that defy all known categories. The light from the entire system will dip or surge in ways that are completely unpredictable, following no discernible pattern of timing, duration, or intensity. These are not the clean, symmetrical curves of a stellar eclipse, nor the sharp, energetic profile of a superflare. The light curves for these events look chaotic, almost alien, as if the system itself is breathing in a way we cannot comprehend. One star might gradually fade over several weeks, only to snap back to its original brightness in a matter of hours. Another might flicker erratically for days, like a damaged street lamp on a cosmic scale. The data presents a puzzle with pieces that simply do not fit our current models of stellar behavior. The most logical explanations fall short. Could it be an unknown type of hypermassive starspot, a vast dark blemish rotating in and out of view? Perhaps, but the temperature changes inferred from the light are often too extreme for a simple cool spot. Maybe it is the occultation of a star by a colossal, disintegrating planet or a cloud of planetary debris. But the scales of these dimming events are frequently too vast, sometimes blotting out a significant percentage of a star's light for months. This points to something far larger and more structured than random dust. These unidentified variable phenomena suggest the existence of astrophysical processes we have not yet dreamed of. Could we be seeing the shadows of immense magnetic loops, larger than entire solar systems, twisting and reconfiguring in real time? Or perhaps the gravitational lensing effect of a hidden, intermediate mass black hole wandering through the system, momentarily bending the light of a background star in a way that creates a bizarre, unrepeatable flicker. Each unexplained light curve is a message, a signal that within the chaos of 12 suns, the universe is still conducting experiments for which we have not yet written the theory. The beautiful possibility of a world with 12 suns hides a brutal reality for any planet that dares to form. Advanced computer simulations have run the numbers, modeling the gravitational tides within these chaotic systems over millions of years, and the results are a death sentence for stability. The simulations reveal 3 grim fates, and every planet faces at least one. The most common destiny is ejection. A passing star's gravity can act as a perfect slingshot, hurling a planet out of the system entirely at a significant fraction of light speed. One moment it is in orbit, the next it is a lone rogue world, condemned to an eternal, sunless deep freeze in the interstellar void. The second fate is even more final: consumption. A planet on a wild, perturbed orbit can plunge directly into the atmosphere of one of its host stars, vaporizing in a brilliant, final flash as it is torn apart by tidal forces and added to the star's mass. The third possibility is a kind of purgatory, a wildly eccentric orbit. The planet is not ejected or consumed, but its path becomes a long, thin ellipse. It screams past its host star at a blistering proximity, its surface baking and its atmosphere boiling away, only to swing out to an incredible distance where everything freezes solid. This cycle of scorching and deep freezing would repeat every single orbit, creating a world of such extreme thermal stress that even the hardiest microbes would struggle to survive. For life as we know it, which depends on stable temperatures and consistent energy, these environments are a perfect hell. The chaotic gravitational tides ensure that the quiet, billions-year-long incubator that allowed life to flourish on Earth is an impossible fantasy here. A planet in a duodecuple system lives on borrowed time, its existence a temporary and fragile accident in a sky ruled by 12 unpredictable masters. The relentless gravitational pull in a 12-star system does more than distort stellar shapes. It can seize control of a star's very spin. Just as our moon is locked, forever showing the same cratered face to the Earth, a star can become tidally synchronized to its orbit. But here, the situation is infinitely more complex. A star might be locked in a tight binary, perpetually presenting one heated hemisphere to its immediate partner, while the combined gravity from several other stars tugs on its opposite side. Imagine a world with multiple moons, each one forcing a different day length upon the planet. Now scale that insanity up to a star, a colossal ball of plasma being twisted by not one, but several competing gravitational rhythms. It is a cosmic tug of war over the star's rotation. The outcome is a star that might spin at a bizarre, compromised rate, a rotational period that represents an average of the conflicting tidal forces acting upon it. One hemisphere could be locked in a permanent, blazing noon toward its binary companion, its surface superheated by the constant proximity, while the other side, facing the chaotic dance of the other suns, experiences a slower, more variable cycle of light and heat. This synchronization has profound internal consequences. The star's internal dynamo, the process that generates its magnetic field, is driven by its rotation. A tidally slowed spin can weaken that magnetic field, making the star less active and potentially calmer. Conversely, if the competing forces force it to spin faster, the dynamo can intensify, wrapping the star in a cage of furious magnetic energy that leads to constant, powerful flares. A star's rotation is its heartbeat, and in this crowded environment, that heartbeat is set not by its own internal clock, but by the frantic, conflicting rhythms of its gravitational masters. The idea of a habitable zone becomes a cosmic mirage in a sky of 12 suns. In our solar system, this region is a placid, well-defined ring where temperatures are just right for liquid water. But here, the very concept of distance from a single star is meaningless. The habitable zone is not a fixed location. It is a shimmering, shape-shifting volume of space that pulsates and contorts with the ever-changing positions of its stellar masters. As the stars whirl through their chaotic dance, the combined heat falling on any given point fluctuates wildly. A planet might find itself bathed in the gentle warmth of 2 red dwarfs one century, only to be seared by the close pass of a blue giant the next. This is not a stable environment, it is a thermal roller coaster. The zone where water could theoretically exist as a liquid does not hold still long enough for life to take root. It flickers in and out of existence in different parts of the system, a temporary oasis of potential that appears only to vanish as the stellar configuration changes. A world could spend 1,000 years in this golden region, its oceans liquid and its skies clear, only to be flung into a deep freeze or a scorching inferno by the gravitational nudge of a passing sun. The conditions for life are not just rare here, they are utterly transient, appearing and disappearing like patches of sunlight on a stormy sea. This dynamic chaos redefines the very search for life beyond Earth, suggesting that the quiet, steady stability of a single star may be the universe's most precious and rare gift. The serene disk of matter spiraling into a single black hole is a model of simple elegance, but place that same process inside a 12-star gravitational circus and all order vanishes. Accretion disks in these systems are not the flat, steady platters we often imagine. They are warped, twisted, and violently torn structures fed by not one but multiple stellar donors. Imagine a fountain with a dozen hoses all aimed at a central drain, each one turning on and off at random intervals. The disk becomes a chaotic, multi-armed vortex of superheated gas, its geometry changing by the hour. The gravitational pull from passing stars constantly yanks on the disk, warping it out of its stable plane. It can be bent into a shape like a potato chip, or have entire sections of its outer rim sheared off and sent flying into the void. This multi-star feeding frenzy leads to behavior so unpredictable it defies classification. The black hole or neutron star at the center experiences a feast or famine existence. For years, it might receive only a trickle of gas glowing faintly in X-rays. Then, a close pass from another star destabilizes the orbit of a donor star, forcing a massive surge of material to crash down into the disk all at once. This triggers an outburst, a brilliant flare of X-rays and gamma rays that can outshine the entire system for weeks. These are not the gentle flickers of an isolated binary, but violent, system-wide tantrums of energy. This chaotic fueling is the engine behind some of the most extreme objects known, microquasars. These are stellar mass black holes that, thanks to this relentless and clumpy supply of fuel, can launch jets of plasma at nearly the speed of light. Within the confines of a duodecuple system, a microquasar's jets would have to punch through a thicket of gravitational fields and stellar winds, their paths bent and distorted as they navigate the celestial traffic jam. The accretion disk becomes the chaotic heart of the system's violence, a place where gravity, matter, and radiation collide in a spectacular, unpredictable storm. Surrounding our own solar system, the Oort cloud is a vast, silent shell of frozen comets, a graveyard of primordial ice. Now magnify that concept by 12. A duodecuple star system could be enveloped by a single, colossal exo-Oort cloud, a shared reservoir of trillions of icy bodies stretching across light years of space. This would not be a peaceful, distant halo. It would be a gravitational minefield, perpetually agitated by the chaotic dance of its stellar masters. Each time a star swings through the outer reaches of this cloud, its gravity acts like a cosmic cue ball, scattering countless comets onto new paths. Most are flung outward into the galactic void, but a significant fraction are sent tumbling inward toward the system's crowded heart. This creates a permanent, slow-motion meteor shower on a system-wide scale, a constant drizzle of icy planetesimals raining down from every direction. For any hypothetical planet huddled close to a star for stability, the sky would be a recurring source of terror. The steady gravitational nudges ensure that periods of heavy bombardment are not rare, catastrophic events from the deep past, but a regular feature of the environment. A planet might experience a lull for a few thousand years, only to have a distant star's orbit slowly evolve, triggering a new wave of cometary impacts that could last for centuries. Imagine a world where brilliant streaks regularly Chinese letter the multi-sunned sky, not as isolated shooting stars but as a relentless hail of frozen missiles. Some would be small, vaporizing harmlessly in the upper atmosphere. Others, however, could be planet killers, large enough to deliver oceans of water or, just as easily, sterilize a nascent biosphere with the force of their impact. This transforms the concept of planetary habitability once again. A world might orbit perfectly within a temporary habitable zone, its climate temperate and its chemistry promising, only to have its progress reset by a celestial bombardment initiated by a star it cannot even see. The very forces that bind the system together ensure that its inner regions are perpetually seeded with both the building blocks of life and the instruments of its destruction. That constant hail of comets is just one consequence of a sky filled with suns. The space between these 12 stars is far from empty. It is a battlefield of invisible forces. Each star, regardless of its size, blows out a relentless gale of charged particles, a stellar wind flowing from its surface at millions of miles per hour. In a solitary system like ours, this wind streams outward unimpeded into the void. But here, with a dozen stars in close quarters, these gales cannot escape. They slam into each other, creating violent, invisible weather fronts in the depths of space, where the wind from a brilliant blue giant meets the gentler breeze from a red dwarf. A colossal shock wave erupts. It is the cosmic equivalent of two hurricane-force winds colliding head-on. The particles in these winds, mostly protons and electrons, are suddenly decelerated from supersonic speeds and compressed with unimaginable force. This compression heats the gas to temperatures of millions of degrees, causing it to glow fiercely, not in visible light, but in the high-energy fury of X-rays and ultraviolet radiation. These are not gentle boundaries, they are seething walls of incandescent plasma, constantly shifting and reforming as the stars move along their chaotic path. The entire system becomes wrapped in a complex, dynamic web of these collision fronts, a labyrinth of lethal energy that would instantly vaporize any physical object passing through it. This violent interplay of winds sculpts the very space the stars inhabit, carving out vast cavities within the surrounding gas clouds and illuminating them from within. The result is a spectacular nebula that glows with the system's combined chaotic light, a permanent, beautiful testament to the unending storm raging between its 12 stellar hearts. Deep within this gravitational storm, a few stars might find perfect sanctuary. The Trojan star hypothesis proposes an elegant solution to the chaos, where stars themselves can become stable partners in a shared orbit. This concept borrows from a well-known phenomenon in our own solar system. Jupiter, the giant planet, shares its path around the Sun with vast swarms of asteroids. These are not random companions, they are trapped in two specific regions of gravitational balance, known as Lagrange points, located 60 degrees ahead of and behind Jupiter in its orbit. At these precise locations, the combined pull of the Sun and Jupiter creates a stable pocket, a gravitational eddy where objects can reside almost peacefully. In a duodecuple system, this principle could be scaled up to a staggering degree. Imagine a massive central binary pair, two stars locked in a tight mutual dance. A third, smaller star could theoretically occupy the Lagrange point of one of these central stars, effectively sharing the same orbital highway while maintaining a safe, fixed distance. This would not be a star orbiting another star, but two stars gracefully leading and following each other around a common center of mass, forever separated by that crucial 60-degree angle. This configuration provides a powerful anchor within the maelstrom. The Trojan star and its primary are gravitationally locked in a resonant embrace, their motion synchronized in a way that shields them from the disruptive tugs of other stars in the system. It is a cosmic conga line of immense proportions, a rare and beautiful example of order carved from the heart of chaos. Finding such a configuration would be a direct observation of celestial mechanics operating at its most refined, proving that even among 12 suns, the universe has a hidden fondness for harmony. The ghost of a stellar cataclysm lingers in the light of these systems. Astronomers have indeed found compelling evidence that some of these 12 star families endured a supernova, a violent death that forever altered their gravitational fabric. The most telling clue is a runaway neutron star, a super-dense stellar corpse hurtling through space on a path that, when traced backward, leads directly back to a surviving duodecuple system. This neutron star is the remnant of what was once a massive member of the family, a star that lived fast and died young in a spectacular explosion. The physics of such an event in a crowded system are terrifying. A supernova does not just vanish, it violently ejects most of the star's mass in a matter of seconds. Imagine one of 12 dancers in a perfectly balanced troupe suddenly vanishing in a blinding flash, their weight instantly removed from the choreography. The entire system would recoil from this event. The sudden, asymmetric loss of mass acts like a cosmic bomb going off, delivering a powerful kick to the system's center of gravity. Every remaining star feels a jarring gravitational jolt, their orbits suddenly and permanently scrambled. The neutron star itself is often born with a tremendous velocity kick from the asymmetrical explosion, which flings it away on a high-speed escape trajectory. It becomes a permanent exile, a dark, dense reminder of the system's traumatic past. But the supernova's signature is not only written in motion, it is etched into the very atmospheres of the surviving stars. The expanding blast wave from the explosion would have washed over the other members of the system, seeding their surfaces with a specific cocktail of heavy elements forged in the stellar inferno. Elements like gold, platinum, and uranium are created in these cataclysmic events. When astronomers detect unusually high abundances of these metals on the surfaces of stars within a duodecuple system, it is like finding radioactive fallout at a historical site. It is direct chemical proof that a supernova occurred right there in the recent cosmic past, and that these stars were close enough to be contaminated by the debris. This pollution tells a story of shared trauma, a dramatic death that both enriched and disrupted the entire celestial family, leaving behind a runaway corpse and a chemical scar on its siblings as the only monuments to a star that is no longer there. This cosmic butterfly effect places a fundamental limit on our knowledge of the universe. We can never measure the starting positions and velocities of 12 stars with infinite precision, a tiny fuzziness that blossoms into completely different futures over millions of years. To even attempt a forecast, astrophysicists turn to a technique called brute force simulation. They program the laws of gravity into a supercomputer and set the 12 stars in motion, calculating the force on each star from every other star at each fleeting moment in time. They do not run this simulation once, but thousands upon thousands of times, each with a slightly different starting setup. A minute variation in a single star's position no larger than the width of a hydrogen atom scaled up to interstellar distances. The result is not a single prediction, but a vast tapestry of possibilities, a probability cloud of potential futures. Some simulations show graceful, resonant orbits persisting for millions of years, a celestial dynasty holding firm. Others depict a rapid and fiery disintegration, with stars being flung out like shrapnel from a cosmic grenade in just a few 100,000 years. The most fascinating patterns to emerge are not those of order, but the beautiful, intricate structures within the chaos itself. When these countless simulated futures are mapped, they reveal strange attractors, which are not physical objects but preferred patterns of motion that the system is drawn toward, even as it never repeats the same path twice. It is like watching a frantic insect trapped in a glass jar. Its flight path is entirely unpredictable from one second to the next, yet over time, its motion defines the shape of the jar itself. These simulations prove that within the apparent anarchy of 12 suns, there is a hidden, beautiful mathematics, a deep and complex order that governs the chaos, revealing that unpredictability itself can have a predictable structure. The universe itself does not know the ultimate fate of this stellar family, as the future is not pre-written but unfolds from this sensitive, chaotic dance. The very definition of a star in these systems is a slippery concept. One of the most profound observational challenges astronomers face is the unresolved binary, a cosmic trick of the light that forces us to question the most basic count. What our telescopes register as a single, brilliant point in a duodecuple system might not be one star at all. It could be 2 or even 3 stars locked in such a tight, frantic orbit that their light blends into an inseparable pinprick from thousands of light years away. This makes the confirmed tally of 12 stars a moving target, a number based on what we can resolve with our current technology. The primary tool for uncovering this hidden architecture is spectroscopy, the art of dissecting starlight. As these close binary stars whip around each other, their light undergoes a continuous, rapid shift. When one star moves toward us, its light is compressed, shifting slightly toward the blue end of the spectrum. As it swings away, the light stretches, shifting to red. In a single star, this creates a clean, rhythmic oscillation. But when you have 2 stars too close to see, their individual blue and red shifts overlap and interfere. The resulting spectrum is a chaotic, blended mess of moving lines, a telltale signature of multiple stellar identities hiding within one point of light. Untangling this signal is a monumental task. It requires taking hundreds of spectroscopic snapshots over months or years, slowly building up a picture of the orbital dance. The math becomes a puzzle of fitting multiple sets of wobbles together, like trying to isolate the individual melodies of 2 violins playing at once from a single, distant recording. Sometimes the data reveals a pair of nearly identical stars. Other times it uncovers a dramatic mismatch, a massive, hot star bound to a small, cool dwarf, their combined light fooling our telescopes into seeing a single, average sun. This means the confirmed duodecuple system we celebrate today might, with better instruments tomorrow, be revealed as a Duodecuple system of 13 or even 14 stars. The 12th star is not always a definitive member, but often a placeholder for our current ignorance, a reminder that the true depth of these celestial families remains just beyond the edge of our vision. These 12-star systems are more than just celestial wonders. They are galactic time capsules, their every motion and molecule a frozen record of a lost era. By reading this record, astronomers practice a form of cosmic archaeology, digging through the present to uncover the galaxy's deep past. The key evidence is written in the star's chemical DNA, a precise inventory of the elements present in their atmospheres. Stars formed early in the universe's history are metal poor, meaning they contain only trace amounts of elements heavier than hydrogen and helium, which were forged in the first stellar furnaces. A duodecuple system with a very low metal content is therefore a living relic, a surviving fragment from the galaxy's wild, formative youth. Its very existence tells us that the chaotic processes needed to build such complex families were at work over 10 billion years ago. The precise mix of elements acts as a timestamp. For instance, a high abundance of europium or gold points to a specific type of ancient supernova that polluted the star-forming cloud just before these stars were born. It is like finding a layer of volcanic ash in an archaeological dig, a chemical signature that links the artifact to a known cataclysmic event in the distant past. But the star's motions are an equally important part of the fossil record. The specific, chaotic paths they trace today are a direct consequence of the gravitational environment in which they formed. By running their orbital dynamics backward in supercomputer models, scientists can deduce the density and turbulence of their original stellar nursery. A system whose orbits suggest a violent, explosive birth tells a story of a region once dominated by massive, short-lived stars whose death shook the entire neighborhood. Another system with more resonant, stable orbits might hint at a slightly quieter, more structured beginning. Each duodecuple system is a single, intricate data point, a piece of pottery from the galactic dark ages. By collecting enough of these rare artifacts, we can begin to assemble a timeline, reconstructing not just how our galaxy was built, but the specific, violent conditions that allowed for its most extreme architectural experiments. The orbital chaos of 12 suns allows for an architectural design so bizarre it seems almost impossible. Among the most mind-bending hypothetical configurations is the polar system, a celestial arrangement where entire families of stars orbit in planes tilted at severe angles to one another. Picture one tight binary pair whirling around a common center in a flat, horizontal plane like a spinning coin. Now imagine a second binary pair, also tightly bound, but orbiting the same central point in a vertical plane, tracing a path like a Ferris wheel. Their orbital planes are not just slightly misaligned, they are perpendicular, crossing each other at a perfect 90-degree angle. This creates a three-dimensional lattice of stellar motion, a gravitational sculpture of incredible complexity. From within such a system, the sky would defy all earthly intuition. The suns would not travel along a predictable band like our planets along the ecliptic. Instead, they would rise and set from every conceivable direction, some soaring directly overhead from north to south, while others skim the horizon in a wide, lazy arc from east to west. There would be no celestial North Pole, no fixed point around which the heavens turn. The concept of constellations would be meaningless as the stellar patterns would unravel and reform in 3 dimensions, a perpetually shifting geometric puzzle. This polar configuration is not just a visual spectacle, it is a gravitational tightrope walk. The competing pulls from these inclined orbits would constantly try to tug the system into a single, flat disk, the path of least resistance. For this polar arrangement to persist, even temporarily, the stars must be perfectly placed and weighted, their motions locked in a delicate balance that resists the universe's innate desire for flatness. It is the ultimate expression of controlled chaos, a testament to the fact that in a cosmos of infinite possibilities, even the orbits of suns can be arranged into a structure of breathtaking perpendicular beauty. Some of these stars hold a bizarre confession in their light, the spectral signature of an element that should not exist. The element is technetium, a radioactive metal with no stable form. Its atoms are inherently unstable, decaying into other elements with a half-life of just over 200,000 years, a mere blink of time for a star that is billions of years old. Finding it on a star's surface is like finding a lit match in a sealed, ancient tomb. The flame should have burned out eons ago. Its presence is a profound contradiction, a clear sign that the star has been contaminated with a fresh supply of this short-lived element within the very recent cosmic past. The explanation for this impossibility lies in the heart of a stellar partnership. The technetium is forged through what is called the slow neutron capture process, or the S process. This is a method of building heavy elements atom by atom, where an atomic nucleus slowly absorbs neutrons one at a time. In the intense, dense core of an aging giant star, atomic nuclei can swim in a sea of neutrons, occasionally capturing one. If the nucleus becomes unstable before it captures the next neutron, it has time to undergo radioactive decay, transforming itself into a different, heavier element. This slow, methodical process builds a specific family of heavy elements, including technetium. But for that technetium to appear on the surface of a star, a dramatic delivery must have occurred. The star we see with technetium in its atmosphere is not the one that created it. It is the recipient in a cosmic act of transfer. Its companion, a star that has evolved into a bloated giant, cooked the technetium in its own core. Then, through powerful stellar winds or direct gravitational siphoning, it expelled this freshly forged radioactive material, showering its partner with elemental ash. The receiving star's gravity then captured this polluted wind, painting its outer layers with the unmistakable, decaying signature of technetium. This entire cycle, from creation to deposition, must have happened within the last few 100,000 years for any technetium to remain visible. It is a live observation of stellar alchemy in action, a direct glimpse into the real-time recycling of matter between two stars bound in a frantic dance. This complex family of 12 suns might be the universe's crucial stepping stone. For decades, astronomers have mapped a clear hierarchy of stellar groupings, from simple binaries to the sprawling open clusters containing thousands of stars. Yet a profound gap has always existed in that sequence. How does a system evolve from a handful of stars into a vast, gravitationally bound metropolis? Duodecuple systems appear to be that very missing link, the middle ground where a large family has not yet blossomed into a full cluster. An open star cluster is a collection of stars born from the same cloud, but its social structure is loose and temporary. Over hundreds of millions of years, the gentle but persistent gravitational tugs from the rest of the galaxy will slowly pull it apart, scattering its stars to the winds. A duodecuple system is different. Its members are locked in a far more intimate and complex gravitational dance, a series of nested orbits that create a stronger, more resilient bond. It is a system that has achieved a higher level of internal organization, a protocluster that stopped just short of becoming a crowd. Think of it as a large, extended family living in a single, intricately designed mansion, as opposed to a bustling city neighborhood where residents are only loosely connected. The mansion has clear rules with different family units in different wings, all bound by their shared roof and foundation. The chaotic gravitational forces that constantly threaten to tear it apart are the very same forces that forged its intricate hierarchical architecture. This structure makes it far more durable than a simple, disorganized swarm of stars. The existence of these systems proves that star formation is not a simple choice between a small family and a massive city. There is an entire spectrum of celestial communities, and duodecuple systems represent a critical, intermediate phase of cosmic construction. a blueprint for how gravity builds complex structures one star at a time. To truly grasp the fate of 12 suns, you must step inside a digital universe. Scientists build these virtual star systems inside some of the most powerful supercomputers on Earth, machines that perform quadrillions of calculations every single second. Even with this staggering power, simulating a duodecuple system is a monumental task. The computer cannot simply calculate the path of each star. It must calculate the gravitational pull that every single star exerts on every other star at every fleeting instant across millions of simulated years. This is not a single calculation, but a continuous cascading chain of them, where the slightest rounding error can spiral into a completely different future. The simulations run for weeks, sometimes months, their progress a slow unveiling of celestial destiny. What emerges from this digital forge is not a single movie of the future, but a vast library of possibilities. Each simulation, with its imperceptibly different starting conditions, tells a different story. In one, the stars settle into a resonant ballet that lasts for eons. In another, the system tears itself to pieces in a fiery gravitational riot within the first million years. The most fascinating result is the pattern within the chaos itself. When you map the countless possible orbits from all these simulations, they do not fill the space randomly. They trace out intricate, swirling shapes known as strange attractors. These are not physical objects, but beautiful, ghostly blueprints that define the preferred rhythms of the system. It is the mathematical signature of chaos, a hidden order that governs the seemingly random dance. Watching these patterns form is like seeing the universe's own fingerprint, a complex and unique identity for a family of 12 suns, written not in light or matter, but in the pure, elegant language of motion and time. One or two colossal suns often take command of the entire celestial family. This lopsided distribution of mass is not a minor detail. It is the fundamental force that dictates the system's stability and its ultimate fate. When a single star contains 70 or 80% of the system's total mass, its gravity becomes the central anchor, the unmoved mover around which all other motion is organized. The smaller stars are no longer equal partners in a chaotic dance. They become mere attendants, their orbits forced into a more predictable, hierarchical structure centered on the dominant giant. This immense star acts as a gravitational shepherd, its powerful field carving out clear lanes and preventing the smaller stars from perturbing each other too severely. It is the difference between a mosh pit and a formal ballroom dance. In a system of equal masses, every star is a potential disruptor, leading to the chaotic pinball game we explored earlier. But with a clear monarch, the motions become more stately, more constrained. The smaller stars are compelled to orbit at specific, resonant distances that minimize their mutual interference, creating a forced peace under the watchful eye of their massive sovereign. This hierarchy can grant the system a surprising longevity, a temporary reprieve from the self-destructive tendencies of a more democratic arrangement. The dominant star's gravity acts as a dam, holding back the tide of chaos that would otherwise quickly tear the family apart. Yet this imposed order comes at a cost. The evolution of the system becomes tied directly to the life and death of its most massive member. That brilliant, dominant star is living on borrowed time, burning through its fuel at a prodigious rate. When it finally exhausts its hydrogen and begins its death throes, swelling into a red supergiant or collapsing into a supernova, the sudden, violent change in its mass will deliver a catastrophic shock to the entire gravitational architecture. The anchor will have been pulled, and the stable orbits of the smaller stars will be sent spiraling into a new and unpredictable era of chaos. The system's past was defined by the giant's life, and its future will be forged in the giant's violent death. Even the light from distant stars is bent by this gravitational chaos. The combined mass of 12 suns warps the space around them, creating a natural cosmic lens. When a far more distant star, perfectly aligned behind this dense system, sends its light our way, that light does not travel in a straight line. Instead, it follows the curved contours of space-time sculpted by the Duodecuple system's immense gravity. This phenomenon is known as gravitational microlensing. The effect is subtle, not creating the giant arcs and rings seen around massive galaxy clusters, but a temporary, precise brightening of the background star's light. As the Duodecuple system drifts slowly across our line of sight, its gravitational field acts like a shifting magnifying glass. It focuses the background starlight, causing it to intensify over a period of weeks or months before fading back to its normal brightness as the alignment passes. This transient brightening is a direct probe of the system's total mass. The duration and shape of the brightening curve are the key clues. A longer, broader peak indicates a more massive lens. The beauty of this method is its impartiality. It measures all the mass present, both seen and unseen. The light does not care if the gravity comes from a brilliant blue giant or a completely dark black hole. It responds only to the total gravitational pull. This provides a crucial, independent check on the mass astronomer's estimate by watching the star's orbits. If the microlensing measurement yields a much higher mass than the visible stars can account for, it is powerful evidence for that hidden component, the dark monarch or the knot of dark matter lurking at the system's heart. It is a silent, elegant confirmation that the true weight of this celestial family is written not just in the motion of its suns, but in the very paths their gravity forces light to take through the cosmos. The silent, spinning heart of a neutron star could be our most precise tool for mapping this gravitational labyrinth. These pulsars, as they are called, are the universe's ultimate timekeepers, born from the supernova death of a massive star. What remains is a city-sized sphere of unimaginably dense matter, spinning hundreds of times every second and firing a lighthouse-like beam of radiation across space with every rotation. If one of these cosmic metronomes exists within a Duodecuple system, its rhythmic pulses would become a direct probe of the warped space-time it moves through. Each tick of this celestial clock would travel to us across a space bent and stretched by the gravity of 12 suns. The path of its radio pulse would be subtly delayed when it passes near a massive star, or accelerated as it flies through a relative gravitational trough. By tracking these minuscule timing variations, deviations of mere milliseconds over years of observation, astronomers could reverse engineer the entire gravitational landscape. It would be like listening to a perfectly steady drumbeat echoing through a complex hall of mirrors, and from the faintest echoes and delays, being able to map the exact shape and position of every single mirror. A single pulsar here would allow us to weigh every star in the system with breathtaking accuracy, simply by measuring how its pulse is pulled and pushed by their invisible hands. We could even detect the presence of those hidden black holes or dark matter clumps, not by the light they emit, but by the silent, rhythmic hiccup they impose on the pulsar's otherwise perfect beat. The search for these natural clocks is a hunt for the ultimate witness, a stellar corpse whose relentless spin holds the key to measuring the invisible architecture of chaos itself. The end of this celestial dynasty is written in a grammar of collisions and expulsions. Over spans of time that dwarf human history, the gravitational pinball game within a Duodecuple system must reach its final logical conclusion. The temporary stability carved out by orbital resonances and mass hierarchies cannot last forever. The relentless gravitational interactions, those subtle nudges accumulated over millions of orbits, slowly but surely push the system toward a series of dramatic finales. The first stars to go are often the smallest, the red dwarfs on the system's fragile outskirts. A close pass from a more massive pair can easily slingshot them out into the galactic darkness, their faint lights vanishing from the family forever. This gradual evaporation pares the system down, reducing the number of players and simplifying the chaos, but also concentrating the remaining gravitational energy into a tighter, more violent core. Within this shrinking heart, the remaining stars are drawn closer together, their orbits tightening and their close encounters becoming more frequent and more dangerous. This is when mergers begin. Two stars in a tight binary, their orbits pumped to high eccentricity by the Kozylidov mechanism, might finally cross a critical threshold. Instead of swinging apart after a close pass, their surfaces touch. The result is not an explosion, but a rapid, messy coalescence. The two stars spiral into each other, their gaseous bodies merging into a single, larger and hotter star. This new hybrid sun is now the dominant gravitational force in its immediate vicinity, but it is also a ticking clock. It has more mass, so it burns its fuel faster, living a shorter, more brilliant life. This process can cascade. The newly merged star might itself engage in a gravitational dance with another massive partner, leading to another merger. Over cosmic time, the system could witness several of these stellar unions. Picture a series of cosmic marriages, each one creating a more massive and unstable heir to the chaotic throne. The ultimate product of this consolidation could be a single, monstrous supermassive star, a behemoth containing the combined mass of several of its original siblings. Such a star would be tremendously luminous and profoundly unstable, racked by powerful winds and violent pulsations as it struggles to hold itself together against its own immense gravity. Its fate is sealed. It will live for only a few million years before its core collapses, initiating a supernova of staggering power. But in the densest, most chaotic systems, there is another, even more extreme possibility. If the merger cascade happens quickly enough and the resulting supermassive star is sufficiently heavy, it might skip the supernova stage entirely. Instead of exploding, its core could collapse directly into a black hole, a gravitational sinkhole with a mass tens or even hundreds of times that of our Sun. This would not be a typical stellar mass black hole, but something rarer and more formidable, an intermediate mass black hole. This object would then sit at the vacant center of the system, a dark monarch ruling over the few surviving stars. Its immense gravity would dictate their final motions, perhaps slowly pulling them in to be consumed, or flinging the last stubborn members away in one final gravitational purge. The once teeming family of 12 suns would end its story not with a brilliant flash, but with the silent, dark dominance of a single, invisible heart. We exist under a single, gentle sun because we could not exist anywhere else. The profound instability of a multi-star system is not just a scientific curiosity, it is a prerequisite for our own reality. This is the anthropic principle, a philosophical lens that turns our cosmic location into a profound statement. The principle suggests that the universe must have properties that allow observers to arise because we are here to observe it. We do not find ourselves on a world with 12 suns because such a place is fundamentally hostile to the long-term, stable conditions life requires. Our quiet solar system is not a cosmic average, it is a rare sanctuary. Imagine a universe filled with countless star systems, a vast lottery of gravitational possibilities. Most of the tickets are for chaotic, multi-star arrangements, places where planetary orbits are short and violent. A tiny fraction of the tickets, perhaps 1 in a billion, are for stable, single-star systems with wide, clear orbits. Now, where would you expect to find a winning ticket? Only in the hand of a winner. We are that winner. Our existence is the selection effect. We are not observing the universe from a typical place. We are observing it from the only kind of place that could have produced us. The relentless gravitational tides, the sterilizing radiation from superflares, the constant threat of ejection or collision, all of these factors make a duodecuple system a factory for dead worlds. For life to emerge, evolve, and persist over billions of years, a planet needs a steady energy source, a stable climate, and protection from frequent extinction-level events. A single star provides that quiet consistency. The chaotic beauty of 12 suns is therefore a spectacle we can only admire from a safe distance. Our very presence as observers is a testament to the fact that our cosmic neighborhood had to be this calm. This shifts our perspective from asking why our system is so simple to understanding that its simplicity is the very reason we are here to ask the question at all. The universe may be capable of immense and spectacular chaos, but we are the products of its most profound and necessary peace. We are standing on the verge of a new era of cosmic revelation. The next generation of observatories, both in space and on the ground, are poised to turn these 12-star puzzles from theoretical marvels into observational certainties. The James Webb Space Telescope, with its colossal golden eye, sees the universe primarily in the infrared part of the spectrum. This is the key that unlocks the hidden details of these chaotic systems. Infrared light pierces through the veils of warm dust that shroud stellar nurseries, allowing Webb to peer directly into the hearts of forming duodecuple systems. It can dissect the light from each individual star in a tight cluster, analyzing their atmospheric chemistry to find those telltale signs of stellar vampirism and chemical pollution. It will see the faint, smoldering glow of the brown dwarfs that have so far remained hidden, completing the system's true census, but the view from the ground will be equally transformative. The extremely large telescope, or ELT, being built in the high deserts of Chile, will possess a mirror so vast it will gather more light than all of the major historical telescopes combined. Its primary power is resolution, an immense clarity that will begin to resolve those unresolved binaries. What we see today as a single, brilliant point will, through the ELT's eye, split into 2 or even 3 distinct stars, instantly increasing the known population of these systems. It will directly image the warped and tortured accretion disks around hidden black holes and trace the subtle orbital wobbles that betray the presence of dark matter. These are not incremental improvements, they are leaps into a new dimension of sight. We will no longer be inferring the chaos from flickering light curves. We will be watching it unfold in real time, star by individual star. The 50 strange discoveries we have catalogued are merely the preface. The next decade promises to multiply that number, revealing architectures of gravity so bizarre they will force us to rewrite the textbooks on how star families are born, live, and die in the crowded heart of the galaxy. This cosmic chaos resonates with something deep within our own imagination. Long before astronomers confirmed their existence, duodecuple star systems were a staple of science fiction, a symbol of the ultimate alien sky. Think of Tatooine's twin suns from Star Wars, a simple binary that immediately signaled a world far from our own. That image is so powerful because it taps into a fundamental human wonder about different skies, different rules. Modern novels and films have taken this much further, envisioning worlds with 3, 4, or even more suns, where civilizations must adapt to permanent daylight or unpredictable seasons. These fictional depictions are more than just spectacle. They are thought experiments about life in a universe that is not built for our comfort. They explore what culture, religion, and even consciousness would become under a dozen different celestial masters. The public is captivated because these systems represent the pinnacle of cosmic complexity and beauty, a perfect storm of physics and art. They are the universe's most extravagant creations, where the simple, predictable rhythms of a single star are replaced by a symphony of gravitational forces. There is a terrifying grandeur to the idea, a sublime mix of awe and fear. We are drawn to them for the same reason we are drawn to the deepest oceans or the highest mountains. They represent a frontier that challenges our understanding and expands our sense of what is possible. They prove that reality can be far stranger and more magnificent than anything we could invent, a celestial drama of 12 suns dancing on the edge of forever. This brings us to the final and perhaps greatest mystery of all. After 50 strange discoveries, one question towers above the rest, a puzzle that every observation and simulation has so far failed to resolve. Are we simply cosmic tourists arriving at a fleeting moment of peace in the lives of these systems? Is our snapshot of 12 suns a brief, lucky calm in a billion-year storm of ejections and collisions, a temporary alignment that will vanish in a cosmic blink? Or does the very existence of these families point to a deeper truth, a fundamental law of orbital mechanics that we have not yet grasped, a hidden principle that actively encourages such breathtaking complexity? The universe seems to be telling us two contradictory stories. On one hand, our most powerful simulations scream that such arrangements are inherently unstable, destined for rapid disintegration. We watch stars being flung into the void and see the relentless gravitational tides that must, over time, tear these families apart. This evidence suggests we are indeed witnessing a rare and temporary ceasefire in a celestial war. Yet, on the other hand, the systems are here, we have found them. They exist against all odds, their intricate hierarchies and resonant orbits defying the simple math of chaos. This persistent reality whispers that our understanding is incomplete. Perhaps there is a stabilizing mechanism we have not yet identified, a gravitational glue that works only in the most extreme conditions. Maybe the constant interactions themselves, the very source of the chaos, generate a feedback loop that paradoxically fosters pockets of long-term stability. The answer will not just solve an academic curiosity. It will reveal whether the cosmos prefers simplicity or if it has a hidden affinity for magnificent, complex tangles. It will tell us if we live in a universe where such stellar families are doomed accidents, or if they are a natural and perhaps even common expression of gravity's deepest, most beautiful rules. The search for this answer is now the central quest, a mystery written in the light of 12 suns. Our journey through 50 bizarre truths reveals a cosmos far wilder than we ever dreamed. These 12 star systems are not mere curiosities, they are cosmic crucibles, forcing us to rewrite the laws of physics under extreme conditions. They have shown us that gravity is not just a force of attraction, but a sculptor of chaos and a weaver of impossible order. Stellar evolution is not a solitary journey, but a shared, turbulent existence where stars steal life from each other and die in spectacular, system-shattering explosions. The very space between suns is alive with invisible storms, tangled magnetic webs, and the silent, trembling hum of gravitational waves. Each discovery peels back a layer, revealing a deeper, more complex universe beneath. So the next time you stand under a quiet, single moon and look up at the familiar stars, remember the celestial ballrooms hidden in the darkness. Out there, in the galactic core, 12 suns are whirling in a gravity-defying dance, a beautiful, chaotic symphony of light and motion. Their story is a permanent invitation to wonder, a call to keep looking up and asking what other magnificent secrets the cosmos is waiting to reveal.